Ja, dat is goed. Ja,
Ik weet niet hoe ik vind het ook wel interessant. Het is goed om even ja, maar nog niet van de daarin en ik heb niet zo makkelijk extra uitgegeven, maar ik mag niet denken en zo. En dan ben ik zo even zo
Okay, let's start again. Now I want to introduce the concepts that are really fundamental in complexity, and these are the concepts of order and disorder, and from there we will go to complexity. So order, well, like the atoms in a crystal, all of the same atoms, all at the same distances, all under the same angles, it's very regular. So order we associate with regularity. Regularity, you might say, means following certain rules. The rule is that each atom is a distance from the next atom, always the same atom, always the same distance, always the same angle. It follows the rules. That means basically that if you know part of it, if you know those four, you know how all the others will look. You can extrapolate as far as you want. Now, that extrapolation in mathematics, there is a nice concept, so that it's called symmetry. The symmetry means that you take part of a pattern, for example, you take those four and you shift it up, down, in all directions, and you just repeat the pattern. The simplest form of symmetry is called a translation symmetry. So here I have a pattern with one rectangle, one circle, and one square. And that pattern I just shift regular distances, each time in the same direction. That's the kind of pattern you might see in a wallpaper. So that is an example of order. You have a simple pattern which is repeated again and again by some kind of a transformation. Another form of symmetry is the left-right symmetry or the mirror symmetry. The left side is exactly the same as the right side, but mirrored. So order means basically that you need just a small bit of the pattern and you can generate all the rest. Now, let's try to understand it in terms of distinctions and connections. The small part of the pattern, that's let's say the minimum element that you need to start from. In the case of this one, the minimum element is one rectangle, one circle, one square. And then you just need to know how much to shift in this direction, how much to shift it in that direction, and everything else in the pattern can be generated. That pattern, you might say, these are distinctions. You have a distinct rectangle, distinct circle, distinct square, and the rest are connections. If the pattern here is like that, then the pattern there is that, then the pattern there is that. So the if-thens, the connections, tell me that once I know how the initially distinct pattern is, I can repeat it and extrapolate it, and I know everything. So that's the essence of order. Few distinctions, many connections. Once you know the basic distinctions, all the rest can be derived from it, and you can go on as far as the pattern goes. Here's another example, a typical pattern you might find on wallpapers. Here you have both a mirror symmetry left-right, and have a translation symmetry like that or like that. So you need to know actually only that part of the pattern, and that part of the pattern you can derive all the others from it. So that's the essence of order. Few distinctions, many connections. Let's now go to the maximum order. The maximum order would be minimal distinctions, maximal connections. So this is a crystal. Let's imagine that it's not just these 5 rows that are depicted here, but that there are 5 million, 5 billion, 5 trillion of these rows. I have only one distinction actually. In essence, I need to just know one atom, and then I can derive all the rest. So imagine that you have this kind of a material. What's characteristic of that material? It's homogeneous. Each part is similar to each other part. It's homogeneous. It doesn't have any structure except for this one distinction here. If I zoom out, I don't see those atoms anymore. I see just one perfectly flat surface. So let's go to even further order. That means that I even remove this one distinction, this one atom. What do I have then? I have something that's perfectly homogeneous. Nothing is distinct from anything else. What's perfect homogeneity? Emptiness. Empty space is perfectly homogeneous. Every spot of empty space is exactly the same as every other spot in empty space. So the limit of order, the maximum possible order, is emptiness. So we have defined now order as few distinctions, many connections. If we go to the limit of 0 distinctions and infinite connections, we have emptiness. What's called in physics the vacuum, empty space. So let's go to the opposite. The opposite is disorder. So that's a highly ordered pattern. That's a highly disordered pattern. Here, the distances and the angles are exactly the same. Here, the distances and the angles are each time different. Disorder means that if you know one part of the pattern, you can't say anything about the rest of the pattern. No matter which part of the pattern I take, the rest is different. I can't say anything about the rest. So this is typically in physics what you would find in a crystal. That means a solid material. This is what you would find in a gas. That means all the molecules, all the atoms are moving independently. Let me show you an animation. Come on. Why doesn't it? Yeah, that's PowerPoint is always behaving strangely. Come on.
This is highly disordered, Francis.
Yes. Well, anyway, it's not that important. The animation I would show you would be just that you have now these things, but now they are moving, and they're moving all in different directions, with different speeds, with different angles. That's what disorder is. Each part of the system is doing its own thing, has its own properties, has its own movement. But now, let's again do the same and go to the limit. So what is disorder? Disorder are lots of distinctions. Each thing has its own properties, its own speed, its own angle, its own position. No connections. They do not care about each other. They're completely independent. But what is typical of a gas? Air is a gas. It looks empty. It's because it is homogeneous, but not homogeneous in this way. but homogeneous in a statistical way. That means that if I take any volume of air, the exact number of atoms in that volume will not be exactly the same as in an equal volume, but it will be practically the same. That is because statistically it is homogeneous. It's very unlikely to have 2 times as many molecules in one volume of air as in another volume of air. The number of molecules in each volume of air is statistically practically the same. That's something called the law of large numbers. If you take enough different numbers, the probabilities become homogeneous. Which means that this version and this version, if we go to the limit, actually they're both empty. They both are examples of emptiness, it's homogeneity. In the air, if I would really go very close by, there would be individual atoms to be seen, but yeah, the air looks pretty homogeneous, pretty empty. Here is another way to represent it. Both of those things look pretty homogeneous. This is perfect order. This, if you would zoom in, is perfect order. This is disorder, perfect disorder. That means random. That means whether a spot is white. Yes.
So it's empty of information.
It's empty of information because information, we will see later how information is divided. Information means that if you have information about another part, that's the difference that makes a difference. Knowing how that part looks, you would have information about how that part looks. If it is disorder, you don't have any information. If we zoom in on these 2 patterns, we see one that's perfectly regular. Each black has one white, has one black, has one white. Here we see that they are randomly divided. But if you look at the right one from a large enough distance, it also looks practically homogeneous. And I have another video, this time it will work. No. Why? Ah, this time it works for some reason. Okay. That's what used to be called snow on a TV screen. Probably none of you have still seen it, but in old TV stations, the TV got its electromagnetic information via an antenna. If there was a broadcast, it would get an ordered pattern. The electromagnetic signal would form a pattern that would be decoded by the TV as an image. But if there was no signal, then the TV would show something like this. That means there would be just random electromagnetic pulses the antenna would pick up, and the antenna would turn these random pulses into random dots on the image, and random noise, which is what you heard, so-called white noise, noise in which all frequencies of sound are equally probable. So that is, you might say, the image of disorder, this kind of picture, so-called snow. So, but let's now again go to the limits of maximal disorder that corresponds to something that is known in quantum mechanics as the quantum fluctuations of the vacuum. So vacuum is emptiness, empty space. In classical mechanics of Newton, empty space is perfectly ordered. Each part of space is exactly the same as each other part. In quantum mechanics, not. In quantum mechanics, the emptiness is actually completely disordered. It means that each part of space behaves differently from each other part of space. But these differences, they are like the snow you saw on the picture before. They appear and they disappear so quickly that basically you don't notice them. You need very sophisticated methods to notice any difference between the quantum vacuum and the classical vacuum. In practice, the quantum vacuum is as empty as the classical vacuum. The difference is that the classical vacuum is perfect order, the quantum vacuum is perfect disorder. I think I have here a video about. Let's see. Okay, so this is a simulation of the vacuum in quantum mechanics. You see things appear and disappear, but of course this is enormously zoomed out. This happens at such a small scale, the Planck scale, that no instrument can detect that. It's only very indirectly that we can detect that the quantum description of the vacuum is correct. Because it's not exactly the same as the classical vacuum, but in practice they both are empty. So that is why do I emphasize that? Because what I'm wanting to go to is that if we want to understand complexity, we should neither go towards order nor to disorder. Perfect order is emptiness, perfect disorder is emptiness. What's the interesting thing? The thing that are in between order and disorder. And this is a famous concept in complexity theory, that is that complexity is in between order and disorder. They sometimes call it the edge of chaos. On the one side, you have disorder, chaos. On the other side, you have the frozen, rigid order, like in a crystal. The real complexity is when you are neither in the one nor in the other. The crystal is that matter, crystal perfectly ordered. The gas perfectly disordered is that matter. Look at a living organism and you see all kinds of structures and processes at different levels. That is complexity. So complexity, we have to understand, is something that's in between order and disorder. How did we define order and disorder? We said order is maximum connection, minimum distinctions. Disorder is maximum distinctions, minimum connections. Well, then what is complexity? Maximum connections and maximum distinctions. So now we are getting towards some kind of a definition of complexity. That is that it's a combination of distinction and connection. So I can also derive that from the etymology of the word. So the word complexus in Latin is the origin of our term complexity. Complexus is like complicated. It means things that are folded the one into the other. It's like a rope that you make a knot in. Complexus is you have two or more parts that are entangled, that are entwined, that are the one into the other so that you can't separate them. And that is the essence of complexity. On the one hand, you have distinct components. On the other hand, you have connections between the components, and these are essential so that you can't take the parts separate. And that is then, of course, the difference with the classical Newtonian view. In the Newtonian view, there's always the assumption I can take things apart and the essence will be there. Systems theory says if you take things apart, you lose the emergent properties. And complexity will say even more, well, the emergent properties are in a sense all there is. The emergent properties are all these connections between the distinctions that make the whole thing fit together. So we come to this definition of complexity. It's a combination of connections and distinctions. But now, a question that many scientists have been wondering about, can I measure complexity? Could I make some kind of a mathematical definition of how complex something really is? Well, you can't. That's one thing that many people have tried, but there is no definition that is generally acceptable to define how complex something is. And there's one definition that was kind of going in the right direction, and the definition is something is complex if the shortest possible description I can give of it is wrong. That means I cannot give a short description of it. Well, we saw that with order, you can describe an ordered pattern very simply. You just take the smallest element of the pattern and then you repeat. So the description of this atom, where you had all the atoms, the one next to the other, of this crystal, you need very little to describe how that crystal looks. You say, take an atom, put another atom next to it at exactly this distance and repeat. That's all you need to do. So the idea was, if you need a long description of something, then it's more complex. Yeah, the more complex something is, the more distinctions and connections, the longer your description will be. But that definition has two big disadvantages. One disadvantage is, according to this description, a perfectly disordered system would be very complex, because in a disordered system, like with a gas, you have to specify the position and the velocity of each of the different molecules in your gas. So you would need a very long description. And that's not what we mean by complex. Disordered is not the same as complex. A second problem with the definition is the shortest possible description. Yes, but the description in which language? Something that looks very complex, like for example, a fractal shape, often you need just one very simple mathematical formula to describe it. Other things that may seem much simpler can't have any mathematical description of it. Maybe you can describe it in language. You can say, well, I'm in love with somebody. Everybody understands what it means, but try to describe being in love as some kind of a physical property of your brain, you wouldn't be able to do it. It would be extremely complicated. So let's say that was the best attempt at a definition. It obviously doesn't work. There have been other attempts, but usually what this definition is, they work in one very specific domain and not in another. For example, one attempt could be, if you look at a biological organism, well, we know that the organism is coded in the DNA. The DNA is like one long string. So you could look at how long is the DNA of a particular organism. You would think that the longer the DNA, the more complex the organism. And then you find that some simple plants, some simple grass-like plants have DNA that's much longer than that of any human. So obviously, that's not a good measure of complexity. So there have been many attempts like that, but the conclusion is you can't really measure complexity. Why is that? Because I said complexity is if you have many distinctions and connections. Now, can't you just start counting all the distinctions and connections? Not really, because it would be like adding apples and oranges. You would be adding things together that are completely different. An example I give is, in some cases, you can say that one thing is more complex than another thing. Let's say you have a normal bike and you have an electrical bike. Well, the electrical bike has everything the normal bike has, plus a battery and a motor and a couple of other things. So you can say, okay, the electrical bike is more complex than the normal bike. But that's the exception. Let's take two different things. Let's take a helicopter and a plane. Which one of the two is most complicated? I can't say. They have lots of different components that are distinct, that are connected in all kinds of different ways. But how can I say that the components in a helicopter are connected in a more complicated way than those in a plane? I can't say. I can't compare. So that means that we can't have an absolute measure of complexity. But we can say that in some cases complexity has increased. When this complexity increased, you start with a number of distinctions and connections, you add more distinctions and more connections, then complexity increases. It's like the bicycle, you have the bicycle, you add a motor to it, you add connections from the motor to the battery, you're adding lots of distinct components, you're adding connections between these components and the rest of the bicycle, you're adding complexity. So In fact, that's the only thing that interests us in this course. We speak about the evolution of complexity, and we want to understand, does complexity increase during evolution? In order to be able to say that the complexity increases, we should have a measure of complexity that does not say it has complexity level 153. No, we need to say it's more complex than the previous version. And that we can do in some cases. When you have something and you add distinctions and you add connections, then you're increasing the complexity. Yeah.
Then we need to be very careful for what distinctions we make, because sometimes when you make new distinctions, you create arbitrary distinctions. Like within the bike, if you would use it for simply going to school or something, then the complexity of an electrical bike or a normal bike does not make any difference, because you will just be going on a path to school. So it's like an artificial not objective concept. You cannot ground it in anything, so it's very hard.
Yeah, it is one of the problems with distinctions, which was one of the problems that was also pointed out in systems theory. In systems theory, we pointed out that the first operation is you draw the boundary, whatever is inside, you say system, whatever is outside, is environment. But different people can draw different boundaries. That means they can make different distinctions. So distinctions, you can say, are to some degree subjective, because maybe I distinguish between red and green, but somebody who is colorblind does not distinguish between those two. Or as you say, if I'm just going to school, I don't care whether that bicycle has a battery or not. Well, assuming that the battery doesn't help you, you might say, okay, I don't really distinguish. I just jump on any bike and I go to school and I don't care what's inside the bike. What we are interested in essence, is fitness. Evolution creates more fitness. So if you add distinction and connections that make the system fitter, then you can say from the point of view of evolution, it makes a difference. So in that sense, it's not purely subjective. There is an element of subjectivity. You can ignore certain distinctions because they don't reflect what you are interested in. But if that distinction, that connection makes a difference for its survival, then I would say there is an objective element to it. But yeah, it's a good remark.
So the normal bike would be more complex because it increases my fitness more.
Your fitness, but then again, it depends whether you're speaking about your physical fitness or your fitness in terms of getting on time to school. If with the electrical bike you're less likely to be late, then from the point of the school, you would be more fit with the electrical bike.
But then you also have a battery to start loading. Something extra, something that can introduce noise.
Yeah. Yeah, what often happens is that you win some and you gain some, which means that your fitness increases because of certain additional components, additional distinct components, but they may have side effects that are not so positive. So of course, it's always a simplification that I say it increases fitness absolutely. It typically increases fitness within a particular environment. But so let's continue with the notion of complexity growing. So I say complexity grows if distinctions increase and connections increase. Now I can have a term for that. Increase of distinction is called differentiation. Differentiation means that you have things that originally were the same and they start to become different. They start to become distinct. Let's take some examples. You start with a simple society where everybody is working on the fields, everybody is a farmer, and then the society evolves so that some people specialize and some people will just grow fruit and some people will keep cows and some people will make pots. You get a division of labor, which means that different people specialize. Instead of all of them being farmers who essentially have the same skills and the same activities, they differentiate, they become different. But if those people become different in their activities, they also become more dependent on each other. If you have a village with 100 farmers that each have their own fields and their own cows, well, these people don't need each other. They get their food from their own cows and from their own vegetables. But if you now have a village where one farmer is keeping cows and milking them, and the other farmer is growing food, if the cow holding farmer needs food, he needs to go to the other one, and vice versa for the milk. So once you start differentiating, you also start increasing the dependency, which means the different parts need each other more, which means more connection. So more connection, that the second process we call integration. Differentiation means more distinctions. Integration means more connections. So complexification, growth in complexity, means that your system differentiates and integrates. Some other examples, an embryo, that means what you get when you fertilize an egg cell with a sperm cell. An embryo originally is just a ball of cells. The moment the egg cell is fertilized, it starts splitting up, and the cells start multiplying. It's a ball of cells. All these cells are the same. But as the embryo goes into a fetus and eventually into a baby, the cells start to differentiate. Some of the cells become bones, some of the cells become skin, some of the cells become internal organs. The cells differentiate, but by differentiating, they also become more dependent on each other. Because in the end, the bones will need calcium, and the calcium will need to come from the food, and the food will need to be entered by the mouth, and will then have to go to the digestive system. So the cells of the digestive system will need to extract nutrients such as calcium from that, and then the blood cells will need to transport that calcium to somewhere else where it will reach the bones. So you have differentiation and integration. So a body is very complex because it's highly differentiated and integrated. But that is, let's say, the ideal case. Differentiation and integration make your system more complex. What would happen if you have only differentiation and not integration, or vice versa? Only differentiation would mean that the different components become more independent of each other. Instead of working together in a coordinated way, they each start doing their own thing. That's not really complexification, because if they lose the connections, if they start each doing their own thing without caring about the others, you get an anarchy, but now in the negative sense. You get again in that situation that I described as a kind of situation that for a while has been happening in Somalia, where you just have different warlords that each do whatever they want. They don't care about any rules. They just take whatever they can find. That's increase of disorder. So if you increase distinction and lose connection, you create a kind of a chaos, a kind of an anarchy. Now let's take the opposite direction. You increase integration and you decrease differentiation. You reduce the number of distinctions. That you put very strict rules that the components cannot deviate from this way. They all have to behave the same. That's more what you might expect in a totalitarian system, where free enterprise, where free initiative, where free expression are all subdued, and everybody has to say the same thing and do the same thing and follow the same rules. That is increasing order, that's not increasing complexity. So complexification is, you really need both. You need differentiation, more distinctions, and integration, more connections. Only if you have those two, you will speak about complexification. So that's a definition of complexity and the process of increasing complexity. Now there's just one more term that I want to mention, which is often used. We spoke about order, disorder, complexity. We also have the term organization. So that's a little bit, you might say, my definition. It's not that there is really a standard definition of that, but organization I define as structure with function. I have some distinct components that are connected. When I have distinct components that are connected, I have a structure. If that structure not an organization, typically, let's say, a firm, is an organization with a particular structure. There are different people in that firm that have different jobs and that work in a coordinated manner, complex system. But the firm has a particular purpose. The firm wants to make profit by, for example, selling Coca-Cola. That's an organization. I could, in principle, have a complex system without any function. Just a bunch of interacting things that are differentiated. Let's take a jungle, a rainforest. Well, the rainforest does not really have a purpose. It's not as if the rainforest as a whole tries to achieve something. The rainforest is a combination of lots of different plants and animals, each of which is different and is dependent on others because it needs those others to eat or to reproduce. So a rainforest is a very complex system, highly differentiated, highly integrated, but you can't say that it's serving a purpose. So in that sense, you might say it's not an organization, but let's say it's a little bit a question of choice. In some respects, we might say that the rainforest is organized in the sense that the rainforest, to some degree, will keep itself, will maintain itself. So that's a bit subjective, what you want to call an organization, what not. But I think it's useful to speak about an organization when you see that the complex system as a whole has a goal. That's when you speak about a system, about an organization, and not just a bunch of things that are interacting with each other in very complicated ways, like an ecosystem. So yeah, another example, the famous watch, the watchmaker, the example we saw in the beginning. A watch is a complex thing, lots of different bits and pieces that are connected with each other in a very particular way. And the watch serves a purpose, namely it shows you the exact time. Now there are some artists who have made, I don't know how are these things called, where you kind of make a very complicated contraption with all kind of different wheels that are connected to each other, but it doesn't serve a purpose. It's a complex, organized thing, but it's there just to kind of showcase its complexity. You might say it's not serving a purpose. So the one I would call an organization, the other one not. And when we're looking at evolution, we will typically find living organisms which have at least the inbuilt purpose or the inbuilt goal that they want to survive and reproduce. So in that sense, typically when complexity evolves, it will also have the organization, it will also have this purpose, this function. So okay, that will be it for today then.